Yeah, thanks. Thanks to the previous speakers. Since you touched the topic of misinformation, I have a great topic regarding misinformation. There's tons of misinformation regarding quantum technologies. I will try to avoid misinforming you anyway, but I cannot guarantee for sure. So first, let me just start with a bit of background myself and why I'm giving this presentation. I come from a rather mathematical background, and I was very fortunate to spend some of the early years learning from some of the great minds in the mathematical minds of Latvia, like Agnes Hančāns, who work with high school students. It's an inspiration for many of us in Latvia in the mathematical circles, and of course the late Professor Usiņš Martins Freivalds, who introduced me to quantum computing and took me deeper in linear algebra. And I was fortunate to spend at least 1 year studying under Sambains as well, because he arrived in back in Latvia around the time I switched from the industry, switched from academia to industry, and that's where I've been since 2007. I've been in various roles, but I've stayed kind of close to network security questions, though mostly I'm a software engineer on a daily basis, but a lot of stuff regarding security, specifically white box cryptography, where I spent 7 years at White Encryption. But whenever we're talking about microservices or various other solutions, there's always network security. And like currently, I'm working at Latvia's Mobilized Telephones, LMT, and we have lots of very different projects that we're working on, and each one we have different discussions about security. But today I'm gonna talk about one specific part of it, and as how quantum technologies have affected security. And I'm not gonna say all of it because there's too much to talk about it. But I'm gonna show how, as an engineer, I've seen the impact in what way. And when studying at LU, I was fortunate to actually see a quantum computer in real life. And here's a picture of one computer. I'm not sure that's exactly the same one I saw, but it's from the same university. I was lucky to visit Professor Ann Sambains at Waterloo University in like 2007. And this is the Institute of Quantum Computing, where they had already some computers. And this is what a quantum computer actually looks like. It's like, it reminded me of a big boiler. I think there were two quantum computers at that time I was there, but maybe I'm forgetting. And then since then, I worked on cryptography, but occasionally some of the topics, as you'll see later, have come up regarding quantum technologies. And it was a nice surprise last year, was it, or maybe it's just earlier this year, that actually LMT is also collaborating with Latvian University regarding quantum technologies. It's when the academia is working in such next generation technologies, they always want to involve the companies to see if there is some way of making this productizable. I would my personal view, this is far from really real use cases where people would pay, companies would pay money for it. Nonetheless, companies and governments cannot afford to ignore it as either. So here we are. But there's a couple of things I need to say before I continue with the presentation. It's that yeah, whenever I look back and read about quantum technologies, as I don't do it on a daily basis, it's always the same. It's always the same. Trying to understand how it all works, it's not easy. And thus, I take an approach that I simply take those statements for granted. I check the source. I don't try to understand all of it. I try to understand the part that affects me, and that's the main thing. I don't know a lot about it, but I've seen how it affects me. I know my cryptography from that part, and I see what's the impact on it, and that's what I'm going to talk about today. So before we go into the effects, we need to start with explaining some basics. What are we covering here? When we talk about security, there's two layers to talk about. First is the ciphers. This is what is used in Hollywood movies. It's all about crypto ciphers, but it's not, as you'll see, that's not all everything at all. But the ciphers are more importantly, there's two types of ciphers that we need to distinguish when we talk about quantum technologies. There are symmetric ciphers, like AES does. I hope you all have heard of AES. That's probably the most popular cipher used. There's now modern cipher, now Signal and others that I'm not sure what they use under the hood. Haven't checked. Because the protocols consist of many ciphers, many building blocks usually, but AES is probably the most widely used, and AES stands for I don't forgot what it stands for actually, but it's standardized by NIST. It's the National Institute of again, I don't forget the name. It's a U.S. government agency that actually standardizes it, and de facto it works as an internet standard. Although Europe is trying to have their own standards, this is de facto what everyone uses. They follow what NIST says, and the idea is that AES does, and these symmetric ciphers are very performant. For AES, you can buy actually chips that do them at high speeds, but there's caveat to it that you need to deliver the key, because as the title says, it's symmetric cipher. It means it's encrypts and decrypts with the same key. So you can have tremendous speeds, but you need to take care of delivering the keys. The other approach is asymmetric, which sounds great because you don't need to deliver the key. You just have your private key and you give a public key to everyone, and that's it. They can encrypt you, you can decrypt it. The problem is the performance is basically very slow compared to symmetric ciphers, and they actually are used often together. Like if you need to decrypt something large, a typical way might be that you first encrypt it with a symmetric cipher, but then you need to send the key, and for that you use asymmetric cipher to just send the short key. So for the large chunks of data, you use symmetric ciphers and asymmetric ciphers for just small things, encrypting keys or doing signature, something very small. But that's not all what we have in cryptography. There's other functions. Important thing is hash functions. Basically, when you sign the document, what does it actually mean? It actually means you take this big chunk of data, you compute a hash function. That means it's like by definition, it's a secure one-way function, that it is from, like, I don't know, megabytes or whatever the size of something is. You calculate the number, I don't know, 512 bytes or bits, depending on what algorithm you use. And the idea is that it's very hard, infeasible almost, to prepare a different document that has the same signature. If you are into blockchains, you will know a lot more about this part of hash functions, because it can be repeated, but it's breaking it is really challenging. It's not SHA-1 has been broken, is considered broken, and MD5, but modern hash functions use larger keys are not broken, and you can assume if you compute the hash, it will not be easy to find another text that has the same hash. And the idea is that the hash is very short, and thus you can sign it. That means you encrypt it with your private key, and then everyone can verify with your public key. Oh yes, you did encrypt it with your private key. So that is considered a signature. And this is the RSA based. There's DSA. It's relatively similar mathematics to ECDSA. So there's two families here. RSA and DCA talk with if you know, basically with the number theory. It's like you calculate a number modulus. You take like a number m, which considers the message. You make an exponent modulus n. Basically, you do it on infinite. Both are finite fields, but you do it in numbers. In ECDSA is for elliptic curves. That's different finite fields that you work with. ECDSA can be lighter to compute in some cases, but it's still roughly the same idea. And there's MACs, and MACs are like message authentication codes. When you're like streaming a video and you want to make sure it's still the correct video, it's the original one or something like that. The idea is that you continuously calculate the message, and you see all the time that it's the valid message. And it uses a symmetric code, but it's like continuous signature, if you could say it like that. And of course, there's also ways that we need to deliver keys, as I mentioned before. It's like key wrapping when you encrypt a key with another key, or a key derivation when you have initial one key, and then you want to have multiple different keys, so it's harder to actually attack the algorithm. Although it still origins from the same key, using this key derivation to change the keys continuously actually improves the security, because it's just simply harder to guess each individual key. On top of it, there's layers, as I mentioned. Typical layer is digital certificates, and I'm just mentioning this layer to understand how it's used. It's the RSA itself. It's simple, small mathematical element, but it doesn't do anything. That's why you need to build something on top of it. Digital signatures is one of the popular use cases for public key infrastructure. The idea is that you generate this key pair. You have the private key, which you store by yourself, and you have the public key. And the idea is that you store it in a document where you can add whatever data you want, like the vaccination status. That's something that we do today. And then there is an authority that supposedly everyone trusts, or basically you need the other party to trust, not everyone. It's the authority is called a certificate authority, which signs your certificate. Signing a certificate basically means that, again, as I mentioned, you calculate the hash of the certificate of the data that's in the certificate, and then encrypt it with this certificate authority's private key, and then you have, that is the signature, and you simply add it to your certificate. That means that the certificate is signed. Simple as that. And the idea is that you can build these chains of trust. You have like this one certificate that you trust, like, I don't know, Latvian government. We all trust Latvian government. They are a certificate authority. If they sign the document, we trust it. And if the owner of that document again signs something else with this document that it has, that is what creates this certificate chain. Like, you can sign a certificate with another certificate, which signs another certificate, and so on. And then, as long as you can verify all the steps back and trust the original certificate authority, you will trust the certificate that is given to you. One thing is, of course, to think about that, whether you trust or not trust. There might be cases when, okay, someone has lost access to his certificate, or a private key has been leaked. For that purpose, there's these certificate revocation lists, where we simply list which certificates should no longer be trusted. And the idea is that it can be any certificate in the chain. If any certificate in the chain is in a CRL, you don't trust the provided certificate. And as I mentioned later, actually these chains and the length of these chains is actually a big issue nowadays when we talk about modernizing or crypto basics. And let's go through a real case scenario. As working at Encryption, I had to work with DRM engines. And here's a real world scenario. We have Hollywood movie studios, which will provide you a movie to your device. Let's say some movie player, DRM enabled. The idea is that the movie studios have these companies in their servers, and they actually pre-encrypt it, because encrypting is actually takes a lot of resources. Yes, AES is fast, but if you have millions of users who want to watch all these movies, it actually takes a toll on your computing power. So actually, you don't need to encrypt it all the time. You can pre-encrypt it and have that secret key. And the DRM service is what will actually distribute to the key. So you will download the content which is encrypted, pre-encrypted a long time ago from the studio, and the DRM service is the one that will provide you the key. And you see that this mechanism uses both symmetric encryption, like for the movie. It uses public key infrastructure for actually authorizing between the parties. Those are the small certificates. You can see that each party, before communicating, they will check the certificate if I should talk to someone at all before providing credentials or something. And then, of course, the data that exchange is also protected by various means. In this case, is explicitly look down what happens to the encryption key and content, but there's, of course, a lot more exchange happening. But we're going to get back to the scenario later a bit. So that is the computer cryptography basics. Now look at the quantum computer basics, and I really mean the basics because I will not dig into quantum mechanics in this talk. But the idea is that a key thing you need to understand: quantum computers are not supercomputers. These are special purpose machines. They cannot do anything super faster. No, they have this dramatic speed, but only for specific calculations. And here on the bottom, you can, if you're a bit familiar with linear mathematics, then you can try to understand what happens. We know how conventional computers work. They work in discrete mathematics. That is, you have ones and zeros, and those are like numbers that the numbers on their modulo power of 2. Like you can have 8-bit numbers, 32-bit numbers. You can consider them as float numbers or what, but at the end of the day, you have some bits like 64-bit numbers or whatever length bit numbers, and those, it's finite field, is discrete mathematics. For quantum computers, it's a bit different. Instead of having these ones and zeros, it's mathematically, you would say that you work with these vectors of values, and actually you can, and each of this value can actually take any number between 1 and 0. This might not be the best case because this only has ones and zeros, but real states can have anything in between. And then you work with these vectors, and you can multiply them by matrices. That is what the quantum computer does. Essentially, of course, there's a lot more details, and I'm not going to go into details, but that shows that there's specific things that you can do a lot faster. But it only really gives you the benefit if you have a lot of these qubits that are entangled together. Like in this case, you can see there's 2 qubits entangled, and there's like 4 different states. We can emulate that with a PC, and it will not give much advantage. You need a lot of these qubits together to actually have a real advantage. And this there have been cases when, for specific tasks, the quantum supremacy has been proven by IBM. That was, I think, last year, if I remember correctly. That means that there was a quantum computer that solved one problem faster than a conventional computer. Of course, it was arbitrarily chosen task, but nonetheless, it shows there is some progress, but there's still ways to go. Currently, best that I found today, at least, is 66 qubits. There's companies who announce a lot of stuff, as I mentioned, a lot of misinformation. So I cannot check whether this is true. I understand this 66 qubit computer is assumed to be true. If anyone has more, I'm not sure. But for practical applications, we need millions of qubits. So you see the difference? 66 millions. Yeah, there's long ways to go. But that doesn't mean there's no threat. So let's look at what it actually means. Well, it's still in early stages. Yeah, it's been decades since mathematics started looking into this, and it could be still decades till we have something feasible. But there is this concept of future proofing, because there are probably government secrets that if someone finds out in 20 years or 30 years, it's still bad. So we need to start looking at it today. And for some cases, we don't know when the quantum break will happen, and we need to be prepared. And the thing is that it's currently what they can do is they can do factorization and calculate these discrete logarithms. That means these are asymmetric key algorithms like RSA, Diffie-Hellman, or basically all of elliptic curve cryptography can be broken, those standard algorithms. But AES, on the other hand, other symmetric algorithms, they cannot be broken like that. Their security is lower than for classical computers. You can see in the table below, like in classical computers, I'm not sure this table is correct because AES-128, the best attack takes less than 128 iterations, but still, if it's roughly 128 bits of security, for commodity computers, it's considered like 60 bits of security. And you can see it's still usable. You just take AES-256 and you have lots of bits of security. But for RSA, it's a different game. You can see that RSA, you need a whopping, I don't know, 15,000 bits, and you still only get 31 bits of security. And using such a big keys will, yeah, it will be very slow even on modern computers. If you are doing some encryption, decryption, even RAS 4000 bit keys can slow you down if you need to do a lot of it. So you can see that RSA is basically broken if you get those supercomputers. We're not there, but if it's there, it can be broken, and that's the concern that the industry has. So what does it mean? It means that basically, if we get there, all the certificates are broken. That's the first thing, because certificates are basically signatures over signatures over signatures from RSA and ECDSA. That's the simplest thing to break, but it's actually a lot more. You can see that we have the encryption key wrapped with the public key. We see both when sending to DRM service and the user. That's broken, and we would think the encrypted content is safe because it's AES, but it's not, because the encryption key is there on the network as well. You just need to find it there, and then you can use it decrypted. So when you look at the protocols, if the protocol has a weak link, it will be broken eventually. But there's already solutions. This is something from the Second World War era. This is actually a symmetric key cipher, if you would say, or simply one-time pad. That means we have the same encryption key on the both ends, and we simply add it to the content. To have us encrypted like a gigabyte of data, you would need a gigabyte of key, because you simply XOR it together, and that's the encryption scheme. And on the left side here, you can see this table, and it looks like two vinyl plates. The idea is that each vinyl plate is the encryption key. And the idea is that supposedly, I understand the first time they tried it out between US and UK government, so there, first the military had to bring in those plates to the UK. They need to see everything together and hope that, oh, it will work. The idea is that they first need to sync that they're moving in direction. They need to sync that they're in the right frequency so that it actually works. And they need to keep swapping it because each of these plates have only a limited number of the key material. So that's why they have these two spinning wheels. You start with one, and then you need to switch to the other one. Yeah, I'm not sure how they pulled it off. It sounds amazing. But yeah, this is what it looks like, and it's actually secure. It's still secure, because if it's a single-use key, there is no way you can actually decrypt it, and it's been mathematically proven. And it's actually, there's modern equivalents as well. If you look at the military, I don't have any proof, but I'm pretty darn sure that they use the same principle to deliver gigabytes, terabytes of keys from one location to another, and use that for encrypting the most sensitive material. They're not relying on any public key infrastructure because, well, they cannot risk spilling all their secrets. For a lot of stuff, of course, but for the most sensitive stuff, I'm pretty sure this is what they use. And there's a startup in Latvia that I was fortunate to meet, I think last year was it, so there's probably even they got farther. But the idea is that they have this one-time pad machine that they put on the cell phones, and the idea is that they need to first deliver the key. I'm not sure how much information I can reveal publicly, but yeah, if you have lots of these devices, you need to deliver the key initially to them, and then you just use that key material to encrypt the data whenever you're sending over a traditional network. And since, yeah, modern days, you can have gigabytes or terabytes of key material in a small device or SSD disk. That depends on the level of security, of course. If you think about also the physical security of the dice, you might not want to use a simple SSD that might be somehow listened to. But if you only think about the communication in between, yeah, just strap on a big SSD, and you can have a lot of secure communications. But yeah, as I mentioned, key delivery is the problem. You need to somehow physically meet to actually deliver the key. So we see that the quantum computers probably will cause problems in the future, and we need to be future safe against that. So what is the industry responses? Actually, well, there's a mathematical response. We don't need any quantum technologies to respond to it. This is what simply is called post-quantum cryptography. As I mentioned, AES is already secure against, is considered secure against quantum computers. Well, you can also figure out, implement a new asymmetric ciphers to achieve the same goal. And then that is what has been happening for a while. The academia has been working on having these new algorithms that would be secure against quantum computers. And then, well, we don't know, but we're preparing. And NIST, again, it's NIST, the same ones that standardized AES, have already in 2016 announced the call for papers to actually submit the new public key or crypto standards. As you can see, we're closing on the timeline when the draft should be available. And the process is that you send in like a lot of these algorithms, like AES. It was called initially Rindial, and it was named AES as it won the AES competition. And the same was happening here. There's like tons of algorithms that are sent proposed, and they look at how performant they are, how secure they are, because it's not that they're broken, is that scientists look at these algorithms and see which ones are less likely to be broken. That is the question they're trying to answer. Which are likely to be faster, which basically they look at a lot of properties to figure out which algorithms would the industry want to use, because they don't want to have like tens algorithms to use. They want to have one or two that are really secure that they can use in most cases. And of course, a lot of conspiracists say that NIST is also looking for some backdoors. Yes, well, I don't really buy that, but I cannot prove either ways. I was in 2016 also in Black Hat conference. That's a conference for security, and it was interesting to see that there was like post-quantum cryptography talk, and at that time it was pretty clear that, oh, quantum computers, that's way in the future, no one cares about that, but it's an interesting topic. And I was surprised that the room was overcrowded. Like I couldn't find a way to sit down. I had to look over shoulders to see the speaker, and it was before it got popular. Oh, yes, it's the same year that NIST announced it, but it is interesting that it's already in the security circles. It's they're working actively on it. And I have a colleague of mine who used to work with Twitchcryption, who is now in a senior position at Amazon. And he clearly states that they're actually following the competition. They need to implement it. They need to look at the performance, how to roll it out. And in Amazon, there's tons of services, and they need to say, okay, where do we need it? There's a lot of work, and the industry is already preparing for this cryptography, and they're really ready. It's not like, oh, they'll be surprised that quantum computers there. No, we will be switched to different algorithms long before those quantum computers arrive. But as I mentioned before, it's still future security. If something has been encrypted with RSA before, in the future it will likely be hacked. But the question is, does anyone care about that? Because switching, there's lots of things to take in consideration when we're switching to this post-quantum world. First, of course, is yes, we need software support and all the libraries, but there's lots more to it. We need to look at the protocols. As I mentioned, ciphers are building blocks, and I've seen in my experience that some of these protocols are pretty, I'm not sure, messed up, I would say. They're just too heavy, and they're not that well standardized. Like when we look at the credit card companies, they have some specific considerations why they would use something like that. And like if you look, what are the ones? Visa, Mastercard, and what is American Express? I don't know the details, but I'm pretty sure that they don't use the same protocols. It's the same. It's the same basic building blocks, these algorithms, but the protocols they use, they have their own usually. And then that means switching all of them to post-quantum cryptography will be challenging. They will need probably new protocols or change it. It will be very costly to the whole IT industry to switch all that, to implement all that, to test that. Problems will likely happen. It's going to take years, and it's going to be done, but it's not a simple switch. There's also things to consider is the performance. Already, there's a lot of cases where it's if you look at NFRs or mobiles, you want to have a low value, low cost thing, low cost chip. but it needs the computing power actually to do the signatures. And post-quantum cryptography is heavier, and that's why you need to look up how to address the issue. One of the things, as I mentioned before, is the certificate chains. If you have CAs that sign CAs that sign CAs that sign CAs, and on each connection you need to check like 10 certificates, it's very costly. In RSA case, it can be actually pretty cheap because of specifics to RSA, where the public keys are usually simply number 3. It happens to be that, yeah, public key is very short usually in RSA. There's usually 2 values. It's either 3 or it was 65535, I guess. One of those 2 numbers are usually public keys, but the private keys are the long ones. So when you're verifying this RSA signature, it's actually pretty fast. But when we're going to post-quantum cryptography, it's going to be slow. So we need to minimize the number of checks we need to do. Then the question is about special purpose hardware. And then that's one of the things I'm sure NIST is thinking about. Can we do a special purpose hardware for those? That can scale it down a lot. And of course, can we simply use lighter protocols? As I mentioned, there's a lot of these protocols are very heavy, and then maybe we can use this something simpler and more standardized, and that can help a lot. And of course, the question is, do we actually need to future-proof anything? Like in some cases, if you sign that, like let's look at the COVID vaccination certificates. What happens if they will be broken in 20, 30 years? I really don't care, because it will not be important in 20, 30 years. And if we will still have some kind of similar certificates, those will be new in new certificates, and those can use different algorithms. But if the certificate I have today for COVID will get hacked in 20 years, I don't care about that. So that's the thing, is that you don't always need to care about the fact that quantum computers might break the algorithms. It's not applicable in all cases. And then one thing to mention is that it's thought, by definition, it's thought to be secure. And Anna mentioned Wikipedia, and here's the funny stuff. I always also think that Wikipedia is not the most trusted source, but when I looked for this post-quantum cryptography definition, a lot of sources try to define it as secure against cryptanalytic attacks by quantum computers. Well, it's not really proven. It's very hard to prove anything in cryptography. It's more like best effort. If no one can hack it, we consider it secure. That's how it usually works. There's very rare cases when we can actually prove something. So in this case, 1.10 for Wikipedia. And but there's also quantum cryptography. If you look back, we talked about post-quantum cryptography. That is classical algorithms that are secure against quantum computers. But there's also algorithms that we can that use the quantum mechanism. And one thing that this is one of the last things I want to talk about today is quantum key distribution. That is something that is already used and tested. I'm not sure whether it's used in the real scenarios for real data. It's more like for test cases. There are, I understand they're used between some clinics in Germany. There's cases in China, but it's more like in the research phase. But the idea is that you can generate the symmetric key that can be used for symmetric ciphers, which are then quantum secure. Of course, you can use it as one-time pad. Then it's going to be provably secure, and that's what everyone says. Oh, it's quantum key distribution, it's theoretically safe. Well, the bit generation rate, the key generation rate is not fast enough for it actually to be provably secure. It's most likely will still use AES, but it will not rely on RSA to actually do this key agreement. That's the main benefit. And that's what actually drives these hybrid solutions I'm mentioning here lower, is that for authentication to see, oh, if you're really the party I want to talk to, for that we can probably use RSA today, because I consider RSA safe today. So if I can trust your certificate today. Maybe not in 20 years, but today I can trust it. So once I know that it is you, we can use QKD to actually exchange the keys, and then I can send the data to you. So those are some interesting topics to discuss. What is when secure, what is when needed. One thing to mention is that we can also have these signature algorithms for quantum cryptography, but they're really infeasible. I understand there's many different problems. One of the things I'm not sure if there are other algorithms, but at least some of the popular ones are limited use. They can be used like I don't know how many times, but they cannot be used indefinitely like modern certificates, which can use as many times as you want. But yeah, the lesson from this is quantum technologies for cryptography, they're not ready yet, but the QKD, that is something that actually the industry is looking at. But before that, there's one more thing, one more way how to use quantum technologies, and this is a random number generator. Here's an example for those couple math geeks that we have here, I'm sure, is that this is how the ECDSA signature looks like. And you need to look at the right side. This is the actual signature, the R and S, that is the signature that is sent. Z is basically the message. Well, you can see here that it's not really the message. It's like you take a hash, take some bits out of it, and basically that's the message that you sign. And here's the funny part: you need a random number. All the green ones, all the green variables are publicly known, but to sign it with your private key DA. I'm not sure why it's called DA instead of something else, but this is the typical notation. And to sign it, you need a random number. And you see that the random number actually gives you two numbers, x1 and k. And the thing is, if the random number generator is broken, if you can force it to have the same number twice, that means you can simply calculate DA. That means this is not changing. You simply have one variable, you have two signatures, and mathematically you can calculate the value of DA. And there have been attacks based on this, that the attackers somehow one way or the other force the random number generator to act predictably or be broken, and then ECDSA can be broken. So there's also a lot of other cases, but this is just very simple to show why random number generator is critical in cryptography. And then you have these quantum random number generators, which will guarantee to have a good number source. They're very useful. But then last thing, as I mentioned, was going. Recently, we did a experiment with LMT did an experiment with LU MII to actually try to have try to look at the quantum internet. The ideas of quantum internet is that you have these nodes that have quantum links between them. We have some random number generators. We have computers, assuming that random number, these key distributors, those are more expensive than just computers who just need to measure the values. The idea is that you can have some links. You can have nodes in the middle. There's two types of nodes in the middle. I assume people will use trusted repeaters. It's like you take the value, measure it, and you send it further, like in classical computer, because it's likely going to be cheaper. But there are also what's called quantum repeaters. I don't know much about it, so I don't want to spread misinformation. But the idea is that if you use quantum repeaters, you can still have a safe entangled state between two parties with intermediate nodes in the middle. And this way you can create a whole network and have secure quantum links between any two nodes. And I was checking what's the biggest network built so far. Allegedly, in China, they have 700 fibers, 2 ground satellite links, and total distance of more than 4,000 kilometers. As I mentioned, there's a lot of misinformation, and I didn't have time to check it out if it has been independently verified. But there's the technology is there. It is doable. There's also a European Union that's also investing in this direction, and this is where our collaboration with LU MII went under. The idea is that the European Union also wants to build a quantum network. The idea is that they have a satellite. We can have satellite links between countries and have optical cables between various positions. And to do that, we actually need to building. And in this case, in the picture, you can see this is Alice and this is Bob. These are two quantum key generation devices. and you can see the optical cables. I'm not sure which ones are which. They're going out. In this case, it's a small loop here just to test it. And this is some measurement. I don't know what it means, sorry. But the idea is that these two machines will generate these keys. And then what the LU scientists did is simply use that as a source for IPsec keys. They built an IPsec tunnel that simply uses the keys generated by this device. A small proof of concept, but yet they tested it for a more than 30-kilometer link. I'm not sure it was the furthest they went, so I might be wrong on that number. But the idea is that they built a link in that this is where LMT came in. We provided the fibers from the LU MII to our base station and back, and they actually probably did multiple loops. We provided more than one link, so you can actually test actually the limits of it. So yeah, this is a fun project I was involved from the LMT side that we did today. And actually, that is it for today.